So in this video, we want to talk about Riemann sums. So these are kind of the same thing as the left or right endpoint approximations, but they're a little bit more general in that it doesn't have to necessarily be the left or right endpoints. It could be any point in the interval giving you the height. So we'll go ahead and write down the definition first. So let f of x be defined on a closed interval AB, and let P be a regular partition of AB. Okay, so remember, regular partition means that the partition has equal width, right? Every rectangle has an equal width in this case, every width of each subinterval. Let delta x be the width of each subinterval xi minus 1 to xi, and for each I, let xi star, okay, so it's like xi with an asterisk as the superscript, xi star be any point in xi minus 1 to xi. Then a Riemann sum is defined for f of x as the sum from I equals 1 to n of f of xi star times delta x. Okay. So here the xi star, the only real difference with the left and right endpoint approximations is that xi star can be any point, right? So like it could be the midpoint, for example. So we're going to look at upper and lower sums where xi might be the maximum over that interval or the minimum over that interval, etc. So just the general word for this rectangular approximation is what's called a Riemann sum. Okay. Now we can define the area of a curve exactly building off of this definition and incorporating limits into it. Okay. So note that here n is defining how many subintervals you have, right? So what we saw with the last approximations that we were doing with the left and the right endpoints is that as we made more subintervals, as we made finer subintervals with less width, the approximations became better. So we can basically think of this in two ways. Either delta x, we can let it approach 0, meaning we can let the width approach 0, or the more natural way is that we can let the number of subintervals go to infinity. Okay. That will leave us with the exact area underneath the curve. So essentially, if we have an infinite number of rectangles with like almost zero width, right? Like infinitesimal width, that leaves us with the exact area underneath the curve. Okay. So let's go ahead and define that part first. This should be area under a curve. Okay. So we let f of x be a continuous non-negative function. Okay. So this means non-negative means that it is always on the positive side of the y-axis, or 0, right? And of course we can look at area for other functions, but this is just how we're going to start with the definition. So let f of x be a continuous non-negative function on AB, and let the sum of I equals 1 to n of f of xi star delta x be a Riemann sum for f of x. Then the area under the curve y equals f of x, okay, on AB is given by a equals the limit as n goes to infinity of the sum from I equals 1 to n of f of xi star times delta x. Okay. So we take an infinite amount of these subintervals, take the area of each rectangle there, and that leaves us with the exact area underneath the curve. So no longer approximately equals, just actually equals. Okay. Now, actually finding this is a whole nother thing, and we'll need to look at exactly the techniques we need to do for that and the relationship with the derivative. So we'll get to that in a little while. So first things we want to look at are, first of all, just exploring this idea of Riemann sums a little more, because like I said, this idea is very useful when you don't have a defined function. And in statistics, we're often not dealing with a defined function. We're dealing with a set of data, right? So another thing we can do is we can find what's called lower and upper sums. Okay, so this is the more common way to find Riemann sums, is to find lower or upper sums. Okay, so if we choose xi star in xi minus 1 to xi, such that f of xi star is greater than or equal to f of x for all x in the subinterval. So in other words, f of xi star is the largest point, it's the maximum. Right, so let me just write here that this is the maximum. Then the Riemann sum is called an upper sum. Okay. And then, of course, naturally, we can just change this definition around. So if it's the minimum point, then it is a lower sum. Okay. So sometimes this corresponds to the left and right endpoint approximations. like we saw with the x squared function, right? X squared is increasing on 0 to infinity. So the right endpoint approximation was an upper sum, and the left endpoint approximation was a lower sum. So that's kind of how you can decide which point to use. You could kind of look at the derivative, look at if it's increasing or decreasing on that interval, and use that to help pick which point you're using. If you're working with the graph, then it's a lot easier. Or if you just have like a finite set of points, like a data points, and it's not a continuous function in the first place, then you would just use whichever one is the largest. Okay. So it's common to call the upper sum u of x and the lower sum L of x, the capital L like this. Sometimes, especially the L is used as like a cursive L to distinguish it from the left-hand sum. But it usually should be clear based on context, which one you're doing. So if we just do an example here where the example asks us to find an upper sum u of x and L of x for f of x equals 10 minus x squared on 1, 2. Okay. And we let n equals 4. Okay. So if we're going to find an upper and a lower sum, let's try to do it without the graph, first of all. Okay. So first of all, the width of each of the rectangles will always be the same thing. So it's going to be 2 minus 1 over 4, right? The difference of the endpoints divided by n. So the width's going to be 1/4. So essentially the points that we might be looking at are 1 to 1 1/4, which is 5/4, 1 2/4, which is 6/4, which is 3/2, 7/4, and 2. Right, so these are we have like this interval, this interval, this interval, this interval. So those are our 4 subintervals. Now, if we want to know what the max or min is, it would be helpful to know whether this function is increasing or decreasing, because then we might just be able to take the left or the right endpoint. Rather than, you could like look at every single subinterval and find the max or the min in those subintervals using the derivative techniques. So you look at the local max or mins, or you look at the endpoints. So in this case, you would really just be testing the endpoints unless we get the vertex in one of these, which we shouldn't. But anyway, so if we look at f prime, just to get an idea of how this function behaves, this is going to be negative 2x, right? So on 1, 2, this is going to be greater than 0. Or I'm sorry, less than 0, the opposite, right? Because if you plug in 1, you get negative 2. If you plug in 2, you get negative 4. If you really want to do it a sign chart, right, your 0 is at 0. 1, 2 is in this part of it. So you're just looking at the sign chart over here, which would be negative. So it's a decreasing function on this part. So this isn't what the function looks like, but you can just imagine a decreasing function. If you have, your subintervals, then a left endpoint is going to be an over approximation, whereas a right endpoint is going to be a under approximation or a lower approximation. Okay. So in other words, for this one, u of x is equal to L4. and L of x is equal to R 4. Okay. So to do these, we'll need to know what the xy values are at these endpoints, right? So 1, 5/4, 3/2, 7/4, and 2. So, you could just use the decimal forms for a lot of these here. So I'll just go ahead and write what the decimals come out to be for these, so it's a little bit easier to use. Okay. This one should be 6 because it's 10 minus x squared, remember? Okay, so this is 10 minus 4, and then this one's going to be 10 minus 1, which is 9. Okay. So the upper sum here, all of them have width 1/4, and then, like I said, we're going to use the left endpoint. So we're going to use 9, 8.4375, etc. All right, so 9 plus 8.4375 plus 7.75 plus 6.9375. So that's going to be equal to, I'm getting 8.03. Okay. And then, so hopefully I put that all in right. For L of x, it's going to be 1/4. And now we're using the right endpoints. 7.75 plus 6.9375 plus 6. So this should come out to 7.28. Okay. So we would expect the actual area to be between these somewhere. So the actual area is 7 2/3. Okay, so 7.67 approximately, right? So exactly, not exactly, but almost exactly halfway between these two. So, and that's kind of the idea, right? So as you make more and more subintervals, the upper and lower sums will get closer and closer together, eventually converging to the true area as you let the limit go to infinity on the number of subintervals.